Hi everybody, this is Dr. Nageswara, Assistant Professor of Physics, SRR and Xavier Government Degree College, Autonomous Vijayawada. We are discussing different methods to obtain low temperatures. There are mainly three methods we are discussing. One is freezing of temperatures. Second one is Joule-Kelvin effect, or also called Joule-Thomson effect. Third one is adiabatic demagnetization. In the first method, that is in freezing mixtures, we can develop temperatures up to minus 80 degrees Celsius. And the second method, that is by using Joule-Kelvin effect or Joule-Thomson effect, we use porous plug. By using this porous plug experiment, we can develop very low temperatures. The third method is adiabatic demagnetization. By using this method, we can obtain temperatures up to 0 Kelvin, nearly 0 Kelvin. Of course, that is 0.0001 Kelvin obtained by using this adiabatic demagnetization method. So what is this adiabatic demagnetization? We know adiabatic is nothing but that is the process in which the heat does not transfer from system into the surroundings or surrounding into the systems. It is nothing but that change in heat, that is dq is equal to 0. That process is called adiabatic process. Demagnetization is nothing but the removal of magnetic field. Already if there is exist magnetic field, if it is removed, that is called demagnetization. So adiabatically, when demagnetization occurs in the paramagnetic material, we can obtain very low temperatures, that is nearly 0.001 Kelvin. So it has very much importance in low temperature physics. Actually, in 1926, Debye and Giavook developed this theory, that is adiabatic demagnetization using paramagnetic materials. What is this paramagnetic materials? We know there is magnetic materials are three types. One is ferromagnetic material, second one is diamagnetic material, third one is paramagnetic material. We know in ferromagnetic material, when it is placed in magnetic field, it attracts the magnetic line of force into the substance, so that there is intensity of magnetization increases. In case of diamagnetic materials, the such materials will oppose the line of forces, which repels the lines of forces. And third one is paramagnetic materials. This is also just like ferromagnetic material, but whose strength is very less. When these paramagnetic materials are adiabatically demagnetized, we can obtain very low temperatures, nearly 0 Kelvin. You see in this diagram, this is the first diagram, which is original paramagnetic material in the absence of magnetic field. If there is no magnetic field in paramagnetic material, all the molecules are in different directions like this. So due to the different directions of these molecules, the intensity of magnetization, that is I is equal to 0. Intensity of magnetization, we will be represent that is I. By this I is equal to 0 in the absence of magnetic field, because all the molecules are in different directions, so that its magnetic moment is 0. That is magnetic moment M is equal to 0 is nothing but intensity of magnetization I is also 0. And this second diagram shows that in the presence of magnetic field, when the magnetic field is placed along this direction, all the molecules in this paramagnetic material whose direction is also along the direction of magnetic field. So that most of the molecules are in the direction of magnetic field, so that it has some permanent magnetic moment, so that it contains some intensity of magnetization. So when these molecules is aligned into the direction of magnetic field, it is required some work to move into the direction of magnetic field. Of course, due to this movement of molecules whose temperature slightly increases. You see here, this is the principle of adiabatic demagnetization, or a for paramagnetic materials, in which paramagnetic material contains molecules which are lying in disorderly manner, of course, as shown in this figure 1. So in which the magnetic moment or intensity of magnetization is 0, when the substance is kept in a magnetic field, gets magnetized as shown in this second diagram, so that it contains some intensity of magnetization. So to move these molecules in the direction of magnetic field as shown in this direction, some external work is done so that its temperature slightly increases, what I said you. So when this paramagnetic material already magnetized, when it is the magnetic field is removed or demagnetization, then these molecules come into its original direction, that is into the disorderly manner. When these molecules try to come into this original direction, it required some energy. That energy is taken from its internal energy. So that when some internal energy is utilized to going into the original direction, whose temperature decreases. So that is the method behind this adiabatic demagnetization, so that the temperature of the substance decreases. Of course, if the temperature of this substance is already very low, the change in temperature or decrease in temperature is also very, very low. So the experimental setup for this adiabatic demagnetization is shown in this figure. In this, the center material, this is gadolinium sulfate. They are taking by Giavuk and that stem. There is the gadolinium sulfate material. This is gadolinium sulfate material. This is suspended in this vessel A. This is vessel A. In this suspended is vessel A in this like this. Of course, this is surrounded by helium gas and there is connected to the vacuum pump. We know by using this vacuum pump, the air inside this vessel A can be removed. The vessel is surrounded by another vessel that is called B or maybe called Devar flask. This vessel contains liquid helium. This is at 1 Kelvin temperature. It is nothing but the liquid helium is at very, very low temperature. Of course, this vessel B or maybe the hour plus B is surrounded by one more the hour plus, that is a C. It is filled with the liquid hydrogen. Of course, it is nothing but it is liquid hydrogen is nothing but the temperature in the vessel C also very, very less. So in the center, there is gadolinium sulfate. It is placed in the vessel A. And this is surrounded by one more the hour flask B, where the temperature is 1 Kelvin. It is filled with the liquid helium. This is surrounded by one more vessel C. It is filled with the liquid hydrogen. The vessel A is connected with the vacuum pump to remove the air inside of this vessel. And this is surrounded by magnetic poles N and S. By using these NS poles, we can apply magnetic field by strong magnetic field. So the temperature of this magnetic material can be obtained by using these coils. These are the coils where M and A are used to measure the temperature by the susceptibility measurements. This is the experimental setup to get the very low temperature by using the adiabatic demagnetization method. Because initially the vessel A is filled with the liquid hydrogen, or maybe of course that is helium gas. At a low temperature, helium gas is a good conductor of heat. So then what happens if this is filled with the hydrogen gas? The temperature of this gadolinium sulfate is reached 1 Kelvin because that is the hour plus B filled with the helium gas at 1 Kelvin. So because that is helium gas is a good conductor of heat, because this is, we know, this is already at 1 Kelvin of temperature. After some time, the temperature of this gadolinium sulfate is also reached 1 Kelvin because that is a good conductor of heat. Now the magnetic field is on. When this magnetic field is on, these molecules in the gadolinium sulfate is aligned into the direction of magnetic field. So the temperature of this gadolinium sulfate slightly increases. Already this is 1 Kelvin. After applying this magnetic field, the temperature may be reached by 1.1 Kelvin or 1.2 Kelvin. It is slightly increases. But we know already this is filled with helium gas. So again, the temperature of this substance reached 1 Kelvin due to the because of helium liquid is filled in this B, the water flask. So it is already in the magnetic field whose temperature now it is at 1 Kelvin. Now at this moment, the helium gas is pushed out or pulled out by using this vacuum pump. So then what happens? The space surrounded this by gadolinium sulfate is vacuum. Due to this vacuum substance, the heat does not transfer from outside into the inside or inside into the outside. That is called adiabatic process occurs. Now, if this magnetic field is removed, then what happens? These molecules inside the paramagnetic material try to align into the disorderly manner in this area. So then what happens when these molecules try to get into the disorderly manner, it requires some internal energy, or maybe it requires some energy. That is energy is taken from its internal energy. So the temperature of this substance decreases. That is less than 1 Kelvin. So by using this procedure, Giabuk and McDougall obtained a temperature of 0.25 Kelvin. So by using this gadolinium sulfate material, those obtained 0.25 Kelvin. That is not stopped by different research, of course, by different scientists done this experiment and by using different materials. Later, Haas and White using the double sulfate of potassium and aluminum in the place of this gadolinium sulfate. It is nothing but gadolinium sulfate is removed. This is placed by double sulfate of potassium and aluminum. They obtained the temperature of 0.002 Kelvin. Of course, thereafter, Stilnan and Garter using this method by using crystals of chromium and aluminum alum, they obtained the temperature of 0.0014 Kelvin. So this is the very least temperature, that is nearly 0 Kelvin, obtained this adiabatic demagnetization method. So what is the magnitude? How much quantity of temperature decreases using this adiabatic demagnetization mathematically? So now we will observe how much temperature decreases mathematically in this experiment. We know the paramagnetic material is magnetized by placing a magnetic field whose magnetic induction is B, then whose molecules aligned in the direction of magnetic field. And it, of course, it is work done, external work is done. So due to this induction magnetic field, there is the intensity of magnetization I changes to Di. We know the paramagnetic material is placed in a magnetic field whose intensity of magnetization increases. The increase in magnetization is taken as Di. So how much work done? This external work done is equal to B into Di. So that the work done against this material to increase the temperature is dW is equal to BDI. If it is demagnetization, then what happens? The same amount of work is done from its internal energy. So that the work done from its internal energy is minus BDI. So now that it is W is equal to minus BDI, work is done. But we know, according to the first law of thermodynamics, mathematically, dQ is equal to du plus dW. You know, dQ is nothing but an amount of heat given to the system. Du is nothing but change in internal energy. dW is equal to work. Of course, dW, you know, PdV. So that is dQ is equal to du plus dW. But what is the dW? Actually, there is some external work is there, that is PdV. And some internal work is done, that is minus PDI. Thus PdV is due to if there is any change in volume, thus some external work is done, that is PdV. Of course, in this case, there is no change in volume, that is a dV is equal to 0. If we will look into the later. So when we substitute this dw value into this above equation, that is a dq is equal to du plus pdv minus bdi. Of course, I already told you in this adiabatic demagnetization, the dv cannot change. It is nothing but there is no change in volume occurs by using this magnetization method. If there is no change of volume, is nothing but dv is equal to 0. So that dq is equal to du minus bdi. Of course, this is comparable with the other equation, that is Maxwell, first law of thermodynamics, dq is equal to du plus dw. By comparing these two equations, we know this is TDS is equal to du plus pdv. When comparing these two equations, p is equal to minus b and v is equal to I. But from the Maxwell's third thermodynamic relations, dou T by dou P at S is equal to dou V by dou S at P. Of course, this is we know that is in Maxwell thermodynamic relations and thermodynamic potentials we discussed, in which that is P is replaced by minus B and this V is replaced by I. That is when we replace these equations, that is can be written as dou T by dou B at S is equal to minus P is replaced by I, that is minus I there, minus dou I by dou S at P is replaced by B. Of course, it is multiplied and divided by dt. Then dou T by dou B at S is equal to minus of dou I by dou T by dou S by dou T at B. Of course, it is multiplied and divided by t. Then dou T by dou B at S is equal to minus t into dou I by dou T by t into dou S by dou T at B. Of course, but we know from the specific heat relation, that is a CB, that is a specific heat at constant magnetic field, that is CB is equal to 1 by m into dou Q by dou T at B. But we know dq is equal to TDS, that dou Q is replaced by T into dou S, then dou S by dou T at B is equal to CMCB. Because when this value, when substituted to the above equation, dou T by dou P at S is equal to minus T into dou I by dou T at B, and this is a T into dou S by dou T is replaced by MCB. So that dou T by dou B at S is equal to minus T into dou I by dou T by MCB. From this, that is minus T by MCB into dou A by dou T at B. That is dou T is equal to minus T by MCB into dou A by dou T at dou B. That is, this gives the decrease in temperature of the substance due to adiabatic demagnetization. But of course, this shows where minus sign shows the decrease in temperature, but this equation does not give the quantity of temperature, how much it decreases. The susceptibility of the substance can be defined as, we know, that is chi is equal to I by B, where we know I is equal to intensity of magnetization and B is called intensity of magnetic field. The where chi is called susceptibility of the substance, that is magnetic susceptibility. But we know, according to the Curie's law, the susceptibility chi is inversely proportional to temperature. So that chi is proportional to 1 by T, that is equal to C by T. So where chi is equal to I by B and where chi is equal to C by T, when compare these two equations, then I by B is equal to C by T. From this I is equal to C by T into B, where when we substitute this value into the above equation, that is equation 1, The change in temperature dou T is equal to minus T by mCB into dou by dou T of I is replaced by CB by dt. So by taking this by integrating this equation, then integration dou T is T, we know that is a T of minus Ti, that is the final temperature minus initial temperature is equal to minus T by mCB into integration dou by dou T of CB by T and dou B. But we know when we have to take differentiation of this, that is dou by dou T of 1 by T is, we know, minus 1 by T square. So that is minus T by mCB into integration Bi to Bi f, that is minus CB by T square, because we know d by dx of 1 by x is minus 1 by x square. So that the by dt of 1 by t is equal to minus 1 by t square and CB and do B. Of course, here minus into minus plus and t is cancelled. So that t of minus ti is equal to c by mCB into integration B do B, whose limits are Bi to Bf. Where Bi is the initial magnetic field, Bf is the final magnetic field. We know integration B dB is B squared by 2. So that T of minus Ti is equal to C by M CB into T into B square by 2. When we apply the limits, that is the T of minus Ti is equal to C by 2 MCBT, that is a BF square minus Bi square. Where we know already told you BF is nothing but final magnetic field. In adiabatic demagnetization, the magnetic field is removed. That is nothing but final magnetic induction is 0. So this Bf is equal to 0. Then what happens? That is a change in temperature. Tf minus Ti is equal to minus Cbi by 2 mCb T square, because minus is came outside. Of course, where minus shows the decrease in temperature, this change in temperature is directly proportional to square of the intensity of magnetic field. It's nothing but when the intensity of magnetic field increases, the change in temperature is also increases. That is, the fall in temperature is also increases. And this fall in temperature is depending on the initial temperature also. If initial temperature is very, very less, the fall in temperature is very good. So by using this equation, we can determine the change in temperature or fall in temperature in adiabatic demagnetization. Thank you very much.